Alright guys, tonight we are going to be learning about 7.5, which is about exponential functions. By the end of this lesson, you'll be able to graph exponential functions and identify data that display exponential behavior. An exponential function is a function defined by an equation of the form y equals a times b to the x, where a does not equal 0 and b is greater than 0 and b does not equal 1. So we're going to take a look at example 1. We want to graph y equals 3 to the x, and we also want to find the y-intercepts and then state the domain and range. So first to graph, we always want to make a table. For the x values, they picked -2, -1, 0, 1, and 2, but really you can pick any x terms you want. So they took the -2 and plugged it in for x, and they got 1/9. And they did the same thing for -1 and they got 1/3. When they plugged in 0, they got 1. When they plugged in 1, they got 3, and 2, they got 9. So then what they did is they plotted their points over here and then connected them with a line. For the y-intercept, that's again still where x equals 0 or where it crosses the y-axis, which would be 1. The domain is all real numbers, and that is because we can plug in any x term. We can plug in any x term up here, and we would get a y out. The range is all positive numbers, and that is because there is no x term that we can plug into the equation and get y equals 0. So it will never cross that x-axis. It's all positive numbers. Now let's take a look at example 2. It's y equals 1/4 to the x. Find the y-intercept and state the domain and range. Again, they used the same x terms, but you can use any x term you want. When they plugged in -2, they got 16. And then -1, they got 4, 0, 1, 1, 1/4, and 2, 1/16. Now be careful when you plug this into your calculator to put the 1/4 in parentheses so that the whole fraction is raised to that x term. Again, the y-intercept is 1 because that's where it crosses the y-axis. The domain is all real numbers, and that's because you can plug in any x term. And then the range is all positive numbers because there's no x term that you can plug in to get y equals 0. It will never cross that x-axis. So let's take a look at this chart that's on your note sheet. It's graphs of exponential functions. So an exponential growth function would have the equation of the form f of x equals a times b to the x, where a is greater than 0 and b is greater than 1. And then the domain would be all reals, and the range would be all positive real numbers. The intercepts, there would be one y-intercept and no x-intercepts. That's because it won't cross that x-axis. The end behavior, as x increases, f of x increases. As x decreases, f of x approaches 0. And it would have the shape of a graph like this. For exponential decay functions, the equation would be of the form f of x equals a times b to the x, where a is greater than 0, but b is greater than 0 but less than 1. The domain would be all reals again, and then the range is all positive real numbers. It would have one y-intercept but no x-intercepts because it won't cross that x-axis. The end behavior, as x increases, f of x approaches 0. But as x decreases, f of x increases, and it would have the shape of this graph. So now we're going to take a look at number 1. We want to graph the function and find the y-intercepts and state the domain and range. Well, to graph the function, let's start with a table. I'm going to use the x values as -2, -1, 0, 1, and 2, but you can use any numbers you'd like. When I plug in -2, I get 11.1. When I plug in -1, we get 3.3. When we plug in 0, we get 1, because any number raised to the 0 power is 1. When I plug in 1, I get 0.3. And when I plug in 2, I get 0.09. I'm going to come over here and graph it. So -2, 11.1 would be right about there. And then -1, 3.3, 0, 1, 1.1, 0.3, and 2.2.09. After I plot those points, I'm going to connect them with a line and draw arrows to extend that line. Then I'm going to find the y-intercept, which would be 1, because that's where it crosses the y-axis. Our domain would be all reals, because I can plug in any x term into the equation. And our range would be all positive reals, so y is greater than 0. It's never going to cross that x-axis. Now let's take a look at number 2. We want to graph 3 to the x plus 1. Again, we're going to start with a table. So when I plug -2 into this equation, I get 1.1. When I plug -1 into the equation, I get 1.3. When I plug 0, I get 2, because 3 to the 0 power is 1 plus 1 equals 2. If I plug in x equals 1, I get 4. And then x equals 2, y equals 10. I'm going to plot these points. Again, I'm going to connect them with the line. Alright, now we want to find the y-intercept. And that would be 2, because that's where it crosses the y-axis and where x equals 0. Our domain would be all real numbers. And then our range this time would be y is greater than 1. And it's y is greater than 1 because we added 1 to the function, so it kind of just shifted the graph up. So now you're never going to be able to plug in an x where you would get y equals 1. So as your x values decrease, your f of x function is going to be approaching 1. So now I want you guys to go ahead and try number 3, and once you've done that, go ahead and hit play again, and we'll pick up on the back. So now we're going to work with identifying exponential behavior. It is sometimes useful to know if a set of data is exponential. One way to tell is to observe the shape of the graph. Another way is to observe the pattern in the set of data. So looking at a table, something like that. So let's look at the example. We want to determine whether the set of data shown below displays exponential behavior. We would write yes or no and then explain why or why not. So method 1, we're going to look for a pattern. So let's look at the table. As the domain is increasing by intervals of 2, your y values have a common factor of 1/2. So we're multiplying the y values by 1/2 or dividing by 2. So using method 1, yes, this would be exponential because the domain values increase at regular intervals of 2, while the range values have a common factor where we multiplied by 1/2. Since the domain values increase by regular intervals and the range values have a common factor, the data are probably exponential. So that's how we would do it by looking for a pattern. Method 2, we would graph the data. So the graph shows rapidly decreasing values of y as x increases. This is a characteristic of exponential behavior. So as x increases, the y values are decreasing rapidly, and the graphs look like the ones we just graphed earlier. So now let's take a look at exercise 1. We want to determine whether the set of data shown below displays exponential behavior. We're going to write yes or no and then explain why or why not. Well, let's take a look at our x terms first. Those are increasing by 1. And then our y values, they are just adding 5. We're not multiplying by anything to get to the next term. So no, this does not display an exponential end behavior because there's no common factor, there's only a common difference. So the adding 5 is your common difference. It's a linear function. So now let's take a look at number 2. So our x values are increasing by 1, while our y values, to go from 3 to 9, we want to multiply by 3, not 1 thing. We want to multiply by 3. And then again, from 9 to 27, we would multiply by 3. And from 27 to 81, we would multiply by 3. So yes, this one is because the domain values are increasing at a constant rate of 1, while the y values have a common factor. We multiply by 3, common factor of 3. So yes, this would display exponential behavior. So go ahead and try numbers 3, 4, 5, and 6, and we will take a look at them tomorrow. Have a good night.